Hi everybody, welcome to the stream. Everything should be going good. Okay, so today, hello. Yes, I think things are working. So, we've got a lot of questions to do today. Essentially, I'm kind of hoping that people are coming to this because they don't have enough experience doing questions involving conservation of energy. So Chapter 7 is an energy chapter. I chose to summarize most of it a couple weeks ago when we first started talking about energy. But applying conservation of energy to do questions is kind of a useful thing to know and to talk about, and so we're gonna do it. So question: open your black Eric Mazur textbook. It's page 117, question number 7. It goes like this: you throw a stone straight up and then catch it as it falls. Draw an energy bar diagram for the Earth stone system just after the stone leaves your hand, at the top of the stone's path, and just before the stone is back in your hand. All right, so an energy bar diagram. I taught this a few years ago with the energy bar diagram. Essentially, when we did it last year, I did it with the energy bar diagram. And I'm not sure people learn very good with it, so I didn't focus on it this year. You see me drawing them on occasion when we're talking about where energy goes. It's essentially a bar graph. It's a diagram rather than a graph that illustrates where the energy in a system goes. So if the system here is the Earth and the ball. It's a ball, right? Oh, it's a rock. Then the energy in the system, there's going to be gravitational potential energy. The configuration, Earth. The configuration, by configuration we mean the kind of the distance between them, that changes, and that means associated with that is a change in energy. All right, so the kinetic energy initially is very high. The potential energy initially is, I don't know, low. At the top of the arc, though, the speed is 0, so the kinetic energy is low, and the potential energy is high. And then it comes back into your hand, and the kinetic energy is high again, and the potential energy is whatever it started out as. Okay, ta-da! That's question 7. Energy bar diagrams are actually fairly tricky, not fairly tricky, fairly useful for illustrating out concepts. So there's actually a question in here that a few people have been bringing to me. Let me see if I can find it. It's a question on your assignment. Question, is it 18? No. Question maybe 34? No. Maybe question 45? No. Question 57? How about 64, 65? Oh, no, wait, 66. Okay, yeah. So question 66 is a problem on the assignment. I'm not going to do it today because it's on your assignment, so you have to do it yourself. But a few people came to me how to do 66. A lot of you found that it's kind of the tricks you're trying don't seem to work. The computer keeps saying you're getting the wrong answer. So, in this particular situation, I recommend that to try to crack the problem, if you're still having trouble with it, try drawing one of these diagrams for the different aspects of the motion. 66 has a ball that starts to fall, and then here's the ground. So it falls, and then it hits the ground, and then it makes a hole in the ground. Where it comes to a stop. So not moving, totally moving, not moving here. And so the question is, what energy was dissipated in making the hole in the ground? And if you're having trouble with that, try drawing out one of these energy diagrams and being really careful with it, because yeah, I think you can figure it out. It's not rocket science. All right, so 9. We should have a course on rocket science. That'd be pretty fun. 9 goes like this. An elevator might be raised or lowered directly by a winch. A winch is a thing that coils or uncoils rope or wire. Let's draw a winch, Ben. Okay. So here's your tube, and here's the rope going around it. And then this is attached to a motor. And the motor turns the winch, and as it turns the winch, the rope goes back. Okay, so that's what a winch is. If you don't know what a winch is not a little bird. That's not a winch. That's a finch. Okay, but this is physics, not biology. Okay, so it's a winch. As in figure 1.9. 1.9 looks like this. This is your winch, and then here's a rope, and here's your elevator. Okay. Or the mechanism might include a counterweight that moves up when the elevator moves down, as in figure B. So figure B, so this is a winch. The other one has some pulleys. And there's another pulley here. And there's a weight here. Oh my gosh. This counterweight system, it looks like an adorable otter. Okay, don't get back to work. In which case is the change in gravitational potential energy of the Earth elevator winch system lower? Oh, I see. Okay, so it's saying that this is a winch. So, in other words, this one turns the rope and forces the rope to go to the left or the right. Okay, hold on. All right, feeling better. Okay, so I understand this question now. In which case is the change in the gravitational potential energy of the Earth elevator winch system lower? So I've been glossing over a lot of these details. You'll notice a question like this isn't on the assignment. The question here asks us to think about systems and whether or not an object is in the system and whether or not the system is closed. So I'm drawing a dotted line around the systems that we're talking about in both cases. There you go, a system. There you got another system. Okay. In which case is the change in the gravitational potential energy of the Earth elevator winch system lower? I think this is a closed system. And this is a not closed system. And I think that's relevant because, okay, hold on. I'll use, yeah, that's a good idea. No, not that color. Green. Okay. Let's talk about if we had talked about this system specifically, the counterweight and the winch and the elevator and also the Earth. Okay. In this case, it's a closed system, and that means energy doesn't leave. The winch still needs to do a little bit of work. The winch needs to consume a little bit of energy to lift the elevator, but in this case, the winch doesn't need to consume all that much energy to lift the elevator because some of the energy required, some of the change in the gravitational potential energy of the elevator is offset by the change in the gravitational potential energy of the counterweight. And that's not the case in this case, in the first one. In the first one, all of the gravitational potential energy, or rather the change in gravitational potential energy, needs to be offset by energy consumed and used up, potential or chemical energy, used by the winch. Okay? So in this case, the winch needs to use less energy to get the elevator up and down than in this case. So this one has winch less, and this one takes winch more energy. Well, that's neat. But that's not what the question's asking. The question's asking about the gravitational potential energy of the elevator. And in the first case, okay, so in this case, the gravitational potential energy is, delta GPE is equal to the energy consumed by the winch. Winch energy, it's plugged into a battery or something. In this case, that's not true. The change in gravitational potential energy is accounted for by the change in the winch energy plus, I'll just go plus, the energy given to the system by the so in the second example, in this example here, the idea is that it's not a closed system. Energy is entering the system from the outside. How's energy entering from the outside? Through the counterweight. The counterweight is giving the system energy. The counterweight's giving the system energy, and that means that the winch doesn't need to do less work. That said, the change in gravitational potential energy of the elevator, I mean, the winch isn't moving in the position of the winch above the Earth isn't changing. I guess the rope's changing, but we assume the rope is massless. So it's the elevator that's changing, and the elevator changes the same in both cases, and so the gravitational potential energy in both cases are the same. And that's the answer to the question. How can they be the same, you might ask? It's a good question. Let me reiterate. One might think that in this case, the gravitational potential energy of the elevator relative to the Earth is less than in this case. And you might think it's less because the winch consumes less energy to work. But that is not the case. because this system here isn't closed. Or rather, this system here doesn't include the counterweight, and because it doesn't include the counterweight, when we're talking about the conservation of energy, we're not accounting for the energy this guy takes in. So if this system included both of them, the changing gravitational potential energy would be less than in this case. But since it doesn't include that, the system uses the same in both cases. That's a weird question. Are you starting to doubt my philosophy of choosing questions kind of at random near the questions in the textbook and then trying to do them on the fly without thinking about the answer? In my opinion, it's good for you to see this because essentially what you're watching is a problem-solving techniques. I'm narrating everything that goes on in my head because essentially when you find yourself in my shoes staring at a problem that you don't know how to solve, you haven't thought about the solution yet, I want you to think about the procedures that I'm using to deal with the problem. Draw a picture. If you're having trouble parsing all the moving parts, draw another picture, right? So, yeah, we're not wasting time. You're learning. Okay, question 19 is about source energy, which is weird because, oh, okay, there's a question, yeah, question 20 is on the assignment, and that involves gasoline. Okay. Choose an appropriate closed system and draw a bar diagram. Oh, another bar diagram. Representing the energy conversion and the transfers that occur in each process of principles checkpoint 7.9. Oh, what's that? I think that's in your white book. What was it called? It's called Principles Checkpoint. What the dog is a checkpoint? You know, I don't see why they can't just write the page. Okay, so I got no idea how to do this question. I don't know what it's referring to. This question must be a mastering physics question. So sometimes they put the mastering physics questions in, and there's like diagrams and interactive details, and then in the textbook they'll just write the text down. I got no idea. What's equivalent to it? Energy bars. Yeah, whatever. Don't worry about it. I'm gonna delete it from the stream list. Is anybody watching this? Oh, look, one person's watching. Hello. So I'm deleting 19 from the list. All right, question 33. Let's do it. 33 goes like this. Oh, sweet, it's a word problem. A 0.01 kilogram bullet fired from a 5 kilogram gun with muzzle velocity 250 meters per second. While the bullet is traveling in the barrel, what's the ratio of the acceleration of the gun to the acceleration of the bullet as a function of time? Oh my gosh. What's the speed of the bullet relative to the ground at the instant the bullet leaves the barrel? And what's the speed of the gun relative to the ground at that instant? Oh my gosh. Okay. I got no idea how to do this question, so I just gave you a sermon on what to do if you don't know. Let's start by drawing some pictures. Okay, so you got your gun. This is what a gun looks like. Here's a bullet. The initial velocities are 0. And then, a few moments later, bullets here. And the bullet's velocity is 250 meters per second. Okay, so it wants the ratio of acceleration of the gun to the acceleration of the bullet as a function of time. Well, okay, let's think about this. This part of it, obviously a momentum question of some sort. And the deal with momentum is P bullet plus P gun is equal to P total. And that's going to be a constant. So 0. Because it's 0 at the start. Okay. So this means P final B plus P final gun is going to be equal to P initial B plus P initial gun. We're asking about acceleration. So I'm going to rearrange this expression in terms of F's and I's. P final bullet minus P initial bullet is equal to P final gun minus P initial gun. Wait, no, signs are wrong. So this is delta P bullet is equal to minus delta P gun, which makes sense. That's conservation of momentum. If the bullet's got increases momentum, the gun's got a decreased momentum. That's what this says. Okay, so then what? What does this have to do with acceleration? So delta mv bullet is equal to minus delta m gun v gun. All right? And the masses of the two objects aren't changing. mb delta vb is equal to minus mg delta vg, and then I can divide them. So delta v bullet is equal to delta v gun minus mg over mb. Right. Okay. So hey, that looks familiar. It should look familiar because it's the that's the law of inertia that we found graphically several weeks ago. Now the question's asking all about acceleration. And the average acceleration is equal to change in velocity divided by time, right? So what if I divide both sides, top and bottom of this, by delta t? EB over delta t. Assume the change of velocity happens over a time interval. It's going to be the same time interval in both cases. So that means the acceleration of b divided by the acceleration of g should follow this rule. Alright, so that's probably the rule they're talking about. Well, the bullet's traveling in the barrel, that's the ratio of the acceleration of the gun to the acceleration of the bullet as a function of time. What's the speed of the bullet relative to the ground the instant the bullet leaves the barrel? Oh, that's neat. So, before we go on, this thing, 250. The number they've given us is the muzzle velocity. I don't know very much about guns. I always kind of assumed that the muzzle velocity was the velocity that it left the muzzle. But the muzzle velocity must be the velocity gun bullet. It's the velocity of the bullet relative to the gun. It's a relative velocity. And that makes sense because there's going to be a kickback. So let's calculate the two. All right, so P total has got to be 0. So that's final velocity of the bullet, bullet final velocity, mass bullet, plus gun final velocity, mass gun. And what else do I know? I know that the bullet's final velocity minus the gun's final velocity has got to be equal to 250. And so I can do a little bit of algebra. And right, V gun final is equal to V bullet final minus 250. Oh, I'm playing fast and loose with these subscripts. That one means it's the bullet final velocity. And right, rather than saying this is the F's velocity relative to the bullet, which doesn't make sense. I'm sorry. It's lawless here. There's no laws for how to write these properly, and I'm sorry. So 0, final bullet. Okay, so I'm called final. The mass of the bullet is 0.01 kilograms plus V final minus 250 times the mass of the gun, which is 5 kilograms. Are guns really 5 kilograms? Never held a gun. I mean, I guess I have. Maybe it's a big heavy gun. So you do some algebra, and so that's 5.01 times V final minus 250 times 5, which is 1250. And I solve algebraically for VF. Hey, Calculon, how you doing? Yeah, there are lots of questions involving guns. I don't know why. 249.5 meters per second. That's the bullet's final velocity relative to the ground. What's the gun's velocity? The gun final. So that's going to be the 250 minus we're using this equation here. It's going to be 249.5 minus 250. So that's 0.5 minus meters per second. It's the velocity of the gun after you fired it. I don't know. This question's weird. I wonder if there's a graph corresponding to it so that you're supposed to find the accelerations off the graph instead of... Yeah, that's probably what you do. You probably look at a graph and figure out what their accelerations are and find their ratio and compare it to this expression. But this is what they're talking about when they talk about their expectation. We'll be seeing this equation shortly in lecture. All right, so that was 33. Oh, 35. A glob of putty thrown to the right bounces off a 0.5 kilogram cart initially at rest on a low friction track. The collision takes 0.15 seconds, and the coefficient of restitution, geez. I don't want to do a coefficient of restitution question. I'm going to change this one. Okay, so let's do, Hey, one person watching, are you there? I don't want to do 35. Do you want to do question 36 or 37? That's the vote. You get to choose. 36. 36 goes, an 8 kilogram object sliding across the ice at blah at some velocity. It explodes, splitting the object into 2 equal chunks and adding 16 joules of kinetic energy to the system. What's the average acceleration of the 2 chunks if the explosive separation takes place over a 0.16 time interval? That's a great question. Another question is, a railroad car, 37 is, a railroad car has some inertia and is moving to the right at some velocity when it collides and couples with 3 identical railroad cars that are already coupled together and moving in the same direction at 2 meters per second. If the acceleration of the single car is blah to the left while it's changing velocity, how long does the interaction take? So you get to choose. One person watching. I'll give you a minute to figure it out. Which one do you want to do? 36 or 37? Your vote determines everything, because you attend these office hours. Let's see, so 35 is gone. So say what you want in the chat. Are you not going to say anything? All right. Okay. Well, the one person watching isn't saying anything. I wonder if the one person watching is me. I don't think so. Okay, you know what? Let's do both. There's something fun here. These questions are interesting because they relate all of the different topics. Kinematics, momentum, and energy together. So let's do one. They're fun. Okay, so 36. An 8.2 kilogram object is sliding across the ice at 2.34 meters per second. It explodes. Splitting object into 2 equal pieces, so I guess they're 4.1 and 4.1 kilograms, respectively, and adding 16 joules of kinetic energy to the system. What's the average acceleration? If delta t is 0.16. So a quick note on how to do it. The issue here is we know the initial velocity of the 2 chunks, right? The initial velocity is 2.34 meters per second for both of them. But we don't know their final velocity. And if you don't know the final velocity, you can't calculate the average acceleration. So how do we do it? You know what? I think maybe in this question, the 2 blobs don't explode in random directions. I think they go like this. 4.1. 4.1. Okay. So there's an easy way to do this question and a hard way to do this question. Let's do it the hard way. We'll call this one V, and we'll call this one U, their respective velocities. Okay, so this is partially a conservation of momentum question. So the initial momentum is of the system. All right, system. I'll call them chunks A and B. A and B, and it's on ice, so it's isolated. 19.2 kilogram meters per second plus, I guess in the i direction. So after the explosion, the velocities are V times 4.1 plus U times 4.1. And in addition to that, we have information about the kinetic energy. Specifically, we know that the initial kinetic energy is 1/2 times 8.2 times 2.34 all squared. All right, 0.34 all squared times 22.4 joules of energy. And then after the collision, the total kinetic energy is going to be, let's see, it said 16 joules got added, right? So it's going to be 22.4 plus 16, which is 38.4 joules of energy. Okay, so 38.4 is equal to the total kinetic energy. So it's going to be 1/2 4.1 times v squared plus 1/2 4.1 times u all squared. So, let me do some algebra to this expression. 38.4 times 2 divided by 4.1. That means that 18.7 is equal to v squared plus u squared. And we also, this is the energy. And then the momentum goes 4.68 is equal to v plus u. Okay. And now we need to solve these algebraically. So, I don't know, let's use substitution. I like writing u. So u is equal to 4.68 minus v. So that's 18.7 is equal to v squared plus 4.68 minus v all squared, which is, oh man, I've been reading this book on ancient mathematics, and it's so frustrating because you're like, just use algebra, and they're like, oh, look at this magic formula we found for calculating the roots of polynomials. It's like, just use algebra. They don't know algebra, so they can't. But if they could, their life would be a lot easier. Oh gosh. All right. This one's supposed to have to be next to it. So that gives us plus, nope, 18.7 minus 21.9 divided by 2 minus 1.6 is equal to v squared minus 4.68v. All right, I'm going to use complete the squares to solve this. You should probably go and use your quadratic formula. All right, so let's see. That's plus 4.68 divided by 2. 5.34 minus 1.6 is equal to 3.74 v squared minus 4.68 times v plus 5.34. All right, and this becomes, you take the square root of that, 1.93 plus or minus is equal to v minus 4.68 divided by 2, 2.34. So v is equal to 2.34 plus or minus 1.93. So it's either equal to 4.27 meters per second, or it's equal to 0.41 meters per second. Meanwhile, U is equal to 68 minus 4.27, 0.41, or it's equal to 4.68 minus 0.41, 4.27. All right. So in this, we have one mass whose mass is, where is it? Where's your mass? 4.1. 4.1. This one's going that way with 0.41 meters per second. This one's going this way with 4.27 meters per second. Let's calculate the total momentum. 4.27 plus 0.41 times 4.1. The total momentum is 19.2. Yay! And the total kinetic energy of the system is plus 4.27 all squared times 4.1 divided by 2. 37.7 joules, which is pretty close. Sig figs. Okay, so good enough. So there's, all right, so that's one way to do it. There's a secret way. You know how we spent so much time on the zero momentum reference frame? Okay. Well, let's draw our pucks over here again. So this one is 8.2. 8.2. And it's moving with velocity 2.34. Okay. And then after the collision, these things have their own velocities. I guess U, V. 4.1 kilogram, 4.1 kilogram. Good. So the secret way to do this is to bring in our observer who we never expected to see again. And we're going to put him in the zero momentum reference frame. So the zero momentum reference frame in this case is him traveling at the same velocity as this thing. 3, 4 meters per second. Okay. So according to observer B, what I'm going to do is the initial momentum is equal to 0. The initial kinetic energy is equal to 0. The final kinetic energy is equal to 0 plus, what was it, 16? 16. 16, yeah. And then, according to this dude, in his view, the rock started off not moving. And then afterwards, you had these two bits moving with, I'll call it UB and VB. Okay? So what are their velocities? According to this person, the total momentum is 0. So if I use conservation of momentum, this becomes 4.1 times UB plus 4.1 times VB. And the kinetic energy is 16 is equal to 1/2 times 4.1 UB squared plus 1/2 4.1 VB all squared. And if you're not paying attention, this equation tells us that UB is equal to minus VB. And that totally makes sense. Conservation of momentum. Both of these objects have the same mass. And so if they start out with 0 momentum, they're going to move with opposite velocities. But that makes this equation pretty easy to solve. 16 is equal to 1/2 4.1 UB squared plus 1/2 4.1 minus UB squared. And you put it together and you get 16 is equal to, click, 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 4.1 times UB squared. So UB is equal to no, do it right. 16 divided by 4.1. 1.98 meters per second. Okay. So I guess UB is going that way, VB is going this way. And then all we have to do is transform back from our weird observer's reference frame to the original one. The original one's moving at plus 2.3 meters per second. So this one becomes 2.34 minus 1.98, 0.36, and the other one becomes 2.34 plus 1.98, 4.32. Yay! These velocities are within what's it called? Sig figs of this. I was playing fast and loose. In this thing, we're dealing with 2 sig figs, so they're right. They're the same. Isn't that fun? So doing it using the zero momentum reference frame actually gives the answer way faster and way easier because you don't have to muck around with all this stuff. Okay, so what do I promise? I promise that we do 37. Yeah, let's try 37. It's fun. Railcar has inertia, big inertia, M. And it's moving to the right, 4.25. Oh, wait, hold on. I didn't even finish the stupid question. The question was, what's their accelerations, right? Yeah, okay. So to find the acceleration, we have to find delta V. So it's going to be V initial, V final minus V initial. So it's going to be, say, 2.34. That's the initial velocity. No, that's the final velocity. 4.32 minus 2.34. So delta V is some cyclic permutation of 4s, 3s, and 2s. 1.98. And that's the average acceleration is delta V over delta T. So we divide that by delta T. 12.4 meters per second squared. Isn't that fun? Yes, it's fun. Okay, right, 37, railroad cars. Oh my gosh. I'm dicking around too much. Quickly now. Wait, maybe I have to do that. We'll see if it gets caught up. Railroad car, it has some mass, and it's moving with velocity 4.25 meters per second, and it collides with some other cars. Which are at rest. And they're moving in this direction with 2.09 meters per second. Okay. So the question goes, if the acceleration of a single car is 5.45 meters per second squared to the left while it's changing its velocity, how long does the interaction take? In other words, if I'm given the acceleration, all right, well, delta V over delta T. What do we know and what don't we know? I guess I'll finish writing this out. V final minus V initial over delta T. What do we know and we don't know? We do know this guy, And we do know this. Nope, it's asking for delta t. We know that one, and we know the initial velocity. So we need to figure out what the final velocity is in order to figure out what delta t is. How do we figure the final velocity? Hey, it's momentum. All right. This is another system that's way easier to do in the well, actually, hold on. It's not that much easier to do. How's this going to work? Here's the deal. This guy is moving. These ones are moving. They're going to attach together. So this guy has little pinchers on it, and this guy has a little thing to get pinched. And when they collide, the pinchers will grab the thingy, and then they'll be stuck together as a super train, moving with some other velocity. Okay? And it's a conservation of momentum question. P total is equal to m times 4.25 plus 3m times 2.09 is equal to 4m times v. And m is equal to, what's it called? 5.04 E4 kilograms. So I plug it all in and solve for v. 4.25 plus 3 times 2.09 divided by 4. Final velocity of the train is 2.63 meters per second. So now I can use this acceleration equation. All right, so the acceleration given is minus 5.45. Final velocity is 2.63. Initial velocity is 4.25. There's delta t. So now I just solve for delta t. 2.63 minus 4.25 divided by 5.45. 0.3. That's how long the collision takes. Isn't this fun? I think it's pretty fun. Obviously, I think it's fun. I just added 2 questions to the assignment, to the question. All right, we gotta add these to the thingy. So we just, instead of 35, we did 37 and 38. So it's kind of too bad. We don't have all that much time to cover all the different possible types of questions that you can already do, given all the things you know. What was I saying? I was saying, like, up above here, I was saying that the nice thing about where we are is we can start to put together all of the concepts and techniques and mathematics that we've learned so far to really good effect. And it's kind of too bad that we don't have more time to do it, because there are a lot of really powerful things that you can do with what you know already from this course. Okay, so let's do question 44. Before I do it, let's see if there's anybody in the chat. Nobody in the chat. All right, 44 looks like this. Non-dissipative interactions, good. 0.36 kilogram cart and a 0.12 kilogram cart are held together with a compressed spring between them. When they're released, the 0.36 kilogram cart moves at 1.1 meters per second to the right. How much elastic potential energy was stored in the spring before the release? Oh, this is a great question. So, what you got here is 2 carts. And there is a spring between them. And the spring is super compressed. So, I think, well, regardless. It doesn't say that the carts aren't moving, but, you know, we can assume they're not moving. Even if they were moving, we could convert to the zero momentum reference frame, and it would look like they started by not moving. So the spring did what springs do. sprung. And these two had velocities. The velocity of this one... Okay, so this is 0.36 kilograms. And this is 0.12 kilograms. That velocity is 1.1 meters per second. And we want to know how much energy the spring had in it before it sprung. So there's two things going on here. There's the conservation of momentum, and there's the conservation of energy. In other words, if the system's cart A and cart B, and the spring, oops, that's a closed system, and so all of the energy will be constant. And initially, the energy is all in potential energy. None of it is at kinetic energy. And then the final state, the potential energy is 0, and it's all in kinetic energy. So if we could figure out how much kinetic energy the two carts had, that would tell us how much potential energy was stored in the spring initially. Okay, so here's the fun bit. We don't know what this velocity is. But, so, we can use conservation of momentum to figure that out. So the P total is equal to 0 because they're not moving. So that means that 0.12 times U plus 0.36 times V, which is 1.1, U has to equal 1 times 0.36 divided by 0.12. 3.3 meters per second. Now I can calculate the total kinetic energy, or the energy final, A plus KE B. It's going to be 1/2 mv squared. 0.5 times 0.12 times 3.3 times 3.3. 0.653 plus 0.87 joules. That's how much energy was in the spring initially. That's fun, right? All right. Next question. 43. Suppose we have a block mounted on a spring, and to find the 0 point for the elastic potential energy of the system to be the relaxed position. Okay, so let's measure from the front of the block. That position is U is equal to 0. What's the appropriate sign for the elastic potential energy when the block is repositioned so the spring is stretched or compressed? In other words, let's say I pulled it, stretched it. What's going to happen to the block? Let's say I squished it, compressed it, spring. What's going to happen to the block? Well, in this system, the block is going to get pulled this way, right? And so when it passes the 0 point line, it's going to have some velocity. So kinetic energy here is positive. The system spring block seems to me to be closed. Energy is not coming out of it going. So if there's kinetic energy here, the potential energy must be 0 when you stretch the spring. What about when you squish the spring? What happens a moment later? You let go, then what? Boing. As the spring passes the u is equal to 0 line, it has a velocity. So at this point in time, it's got non-zero, big kinetic energy. The total energy at this point is kinetic energy plus potential energy is equal to 0. Right? So that means that because it has kinetic energy here, the potential energy over here must be 0. So with the spring system, if I move to the right, the potential energy is bigger than 0. And if I move to the left, the potential energy is 0. That's fun. That's not how gravity works, but it's fun. Okay, so now it's time for 59. Any questions in the question box? No questions in the question box. 59 goes like this. You drop a rubber ball from height 3 meters. It bounces off a concrete surface height 2.7 meters. Okay. Oh, this is another coefficient of restitution question. I don't want to do a question. Whatever. Yeah, I'm not going to do question 59. It's no good. I'll take it off the list. I've been doing questions all day. 58 though is really good, so I'll do 58. Okay, so 58 goes like this. 2 blocks are hung by a string draped over a pulley. A 1 kilogram block on the left and a 3 kilogram block on the right. The 2 blocks start off at rest at the same height. What's the change in gravitational potential energy of the system of blocks and Earth when the 3 kilogram block has dropped 0.53 meters? What's the change in the kinetic energy of the system between release and this instant? What's the velocity of the 1 kilogram block at this instant? That's a good question. Dig it. Oh man, pulley questions are the best. So here's the ceiling, and from it we hang a pulley. You know what a pulley is, right? It's like a round object, and it's shaped like this. It's got a little wheel that it can pivot on, and it can spin. And you attach this somewhere, and you attach this somewhere. And then you put a rope through it. And the nice thing about pulleys is they let you change the direction of a rope without changing the tension force. And also, they roll. And that means that the rope can slide to the left and the right, as it does in this case. Let's draw the 2 blocks. Okay. So, this is a 1 kilogram and a 3 kilogram. And what's going to happen? 3 kilogram block drops. So we'll go to this. We'll go with this height. Okay. I'm trying to set this up as carefully as I can because I know that there's going to be some mucking about with this. So the 3 kilogram block drops a height minus 0.53 meters. Okay, so now the 3 kilogram block is here. And we can put the ground down here. Why not? Okay, so how has the energy of the system, 1 kilogram, 3 kilogram, Earth, how has that changed? Well, this is pretty fun, cause, dig it. Does the 10 kilogram or the 1 kilogram block move? It does. Which direction does it move? It moves up. How far does it move up? It moves up 0.53 meters. How do I know? It's because it's a rope. The rope can't get any longer or shorter. So if this one goes down, this one has to go up. Okay, so I want to know the change in gravitational potential energy. Oh, I think I missed a meeting. Okay, I want to know the change in the gravitational potential energy. So, there's two parts to it. There's the gravitational potential energy of this part and a gravitational potential energy of this part. So, mg delta y plus mg delta y of the two different objects. So the first one's 1 times 9.81 times 0.53, and the other is 3 times 9.81 minus 0.53. So the gravitational potential energy is changed by minus 10.4 joules. Okay. At this moment, the total energy. So initially, the total energy is 0. Well, okay. So initially, I need to define what the total energy is, because why not? Let's set u to equal 0 at this height. I know that the kinetic energy initially is 0, so the total energy should be equal 0. And that means that if the gravitational potential energy goes down by this much, the kinetic energy must increase by that much. Okay, so C, what's the velocity of the 1 kilogram block? Do they have velocities? I guess so. Think about it. This one, let's clean this up a little. This one's moving with this velocity, and this one has to be moving up with that velocity. Is there a relationship between these velocities? Yeah, there has to be. There has to be a relationship between the two blocks because they're tied together with a rope. So just like if this one goes down 0.5, this one has to go up 0.5, their velocities have to be related. This isn't a generically true statement, but this statement is true of this system. So, you know, it's not like a conservation of momentum. It's just because they're attached together with a rope. So what this means is that we can write the kinetic energy as 1/2 times the mass times the velocity squared plus 1/2 times the mass times its velocity, which is minus v all squared, which becomes 2v squared 10.4, so v is equal to 2.2 meters per second. That's how fast they're both traveling. Fun, right? Okay, so that was question 5.8. And for question 65. 65 goes like this. You drop a ball from rest from around 12 meters above the ground. Just before it hits the ground, its speed is recorded by 14.6 meters per second. What percentage of the ball's kinetic energy is dissipated due to air resistance? Okay. So when we're keeping track of energy, the key here is always to go with closed systems, because in a closed system, the total energy is going to be the same all the time. That said, what kind of energy is in the system? Okay, so a closed system here, it's got to be the ball, the Earth, and the air. They just say there's air resistance, so it's got to be in the system. You'll note here that when we talk about the total energy, there's three different types. There's kinetic energy, there's the potential energy from gravity, and then there's air dissipated, the energy in the air. Okay? So to do this calculation, I need to find the total energy initially. And so the kinetic energy is 0. I'm going to assume the air energy in the air is 0. We only care about how it changes. So now I need to rely on a formula for the gravitational potential energy. Where am I going to put U is equal to 0? I'll put it here on the ground because it's useful that way. And that way, at this height here, the gravitational potential energy is mgh. So it's going to be the mass, which is 5.3 times 9.81 times 12. 623.9. So the total energy is 623.9 joules. And then I can say, okay, so finally, I can calculate the kinetic energy because I've been given the speed. So it's going to be 1/2 times 5.3, the mass, times the velocity, 14.6 all squared. Oh, come now. 0.9. The gravitational potential energy at that position is 0. And I don't know how much air energy has been dissipated so far. And so you can set this equal to 623.9 to figure out how much energy has been dissipated. $59 joules. So that's question 65. Let's do question 68 and then call it a day unless somebody has a question in the chat. Nobody has a question in the chat. All right. 68 goes like this. 0.7 kilogram basketball is dropped on a hardwood floor. It rises back to 65% of its original height. If the basketball is dropped from a height of 1.5, how much energy is dissipated in the first bounce? Okay. Here's my ball. Here's my floor. Here's my final. So the initial one here, that's 1.5. And after the first bounce, it's at 0.6 times 1.5. No, so it's 0.65. So that's 0.975. At the peak of its bounce, its speed is 0. The system is the air, ball, the Earth, then that system's going to be closed. So all I need to do is decide where I want u to equal 0. How about if I set u to equal 0 down here on the ground? And that way the gravitational potential energy at these heights. So the total initial energy is going to be, okay, so what kind of energies are there here? There is gravitational potential, there's kinetic, and there's, you know, heat, air. Dissipated energy. So initially, the kinetic energy is 0. Assume the air dissipated, and the gravitational potential energy is at 1.5 times 9.81 times its mass, 0.7. Okay. The ball, after one bounce, at the peak of its height, it's going to have no kinetic energy, air, so all the dissipated energy. I can calculate the gravitational potential energy at that height too, 975 times 0.7 times 9.81, 6.7 joules. So, how much energy is dissipated on the first bounce? On the first bounce, it's 10.3 minus 6.7, 3.6 joules of energy is dissipated on the first bounce. What about the fourth bounce? So, first bounce, second bounce, third bounce, fourth bounce takes us to there. So what are all these heights? 0.975 times 0.65. This is 0.63 meters. 0.63 times 0.65 is, this height's 0.41 meters. And the last one's 0.27 meters. So on the fourth bounce, the gravitational potential energy initial is 0.41 times 0.41 times 9.81 times 0.7. And the gravitational potential energy after the bounce is 0.27, 1.81 times 0.7, 1.85 joules. And so the change in the air is going to be, it's going to be the difference between these. 2.81 minus 1.85. 0.96 joules. All right. To which type of incoherent energy is the distributed and dissipated energy converted? Sound, mostly, I think. Sound, a little bit of heat. Things warm up. Sound and heat. All right. That's it. That's it for this online office hours. Remember that if you have any questions, you can always ask me. The questions I did from the book are a pretty good exercise. Go have fun. Talk to you later. How do I shut this off? I go stop streaming.